Coming up next, an Astronomy.fm original program. It's time for York Universe, a co-production of the Observatory of York University, Toronto, and the Voice of Astronomy.
Hello, and welcome to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'll be one of your hosts this evening. I am Julie Tomei, and I am joined after a hiatus by Connor Hayes. Hi, Connor.
Good evening.
We are broadcasting live from the Allan Carswell Observatory located at York University in Toronto, Ontario, Canada. This is Science Night in Canada, where the lineup is all Canadian, starting with ourselves, York Universe, and then on to Western Worlds, Quirks, and Science for the People. York Universe broadcasts every Monday night at 9 p.m. local Toronto time. That is Tuesday morning at 1 a.m. Universal Coordinated Time. The York Universe production works in concert with our online public viewing program run by the Observatory team, which runs between the hours of 9 and 10 p.m. local Toronto time. So to join that, head over to our website at www.yorku.ca/science/observatory and follow the links to OPV online public viewing, and there you can join the chat. Our broadcast is powered by and in partnership with Astronomy.fm, the voice of astronomy. For any questions or comments you have about our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca, or you can connect with us on the socials. We have a number of different handles, so here we go. On Twitter, we are at York Observatory. On Instagram, we are York U Observatory, and Facebook, we are Allan I. Carswell Obs. I don't know if we have joined Threads yet. All of our programs are free, but if you would like to make a donation, we certainly won't stop you. We, in fact, would welcome it, and you can head over to our website. Once again, that is www.yorku.ca/science/observatory. We'll be monitoring the chat room for any questions or to post content. The current weather is looking pretty nice in Toronto today, looking like a clear sky. So I'm thinking you're going to be looking at some nice, fresh images from the 1 meter telescope if you head over and join the online team for the online public viewing. Yeah. How you doing, Connor?
Been keeping myself pretty busy. I was just finishing up my master's degree the last time I was on here, and now I'm nearly a year into my PhD.
Congratulations.
Definitely meant to show up a bit sooner than this, but life keeps happening, including that aforementioned PhD and writing several papers and shepherding those through that whole occasionally nightmarish process.
Yes. My original plan when I started university was like, I'm going to do a master's and I'm going to do a PhD. And then I met some grad students and I hung out with some grad students and I saw what that entailed. And I was like, nope, not for me. I think I stand by that. Yeah. So maybe one day I will get a master's, but not in astronomy. I am one course and one research project away from a master's in science communication. Someday, I will upgrade that graduate diploma. I just got busy with children and stuff.
Yep, that will do it, I would imagine.
They do take a lot of time.
I have been told this.
Yes, they're lovely, and I wouldn't change them for the world. All right, so let's take a peek. Looks like we're looking at the moon, the Eagle Nebula. Oh, what's the Eagle Nebula? Now it's a great picture of the the Observatory, and M11 over at the online public viewing. We've got Tamila and Sergi throwing stuff up there for folks. So head over there if you feel so inclined. All right, shall we jump into this week in space and astronomy history?
Sounds good to me.
All right, let's do it.
All right, so I guess I will be kicking us off this evening with an event that occurred on July 14th and 15th, 1965, which would be the Mariner 4 flyby of Mars. So just to get started with a little bit of background here, of course, for several centuries, Mars existed in our public consciousness as this sort of mysterious place where intelligent life could exist outside of Earth. This was driven in large part by the fact that the telescopes at the time could not actually view the Martian surface in any significant detail. So the best maps that we had for many years were based on these observations of these sort of vague dark and light patches whose nature was subject to considerable speculation. So this idea of intelligent Martians was popularized in large part by Percival Lowell. This is the same Percival Lowell whose work led to the discovery of Pluto. He published these 3 books between 1895 and 1908, detailing his beliefs in the idea of Martian life. So these books were notable for their maps of the Martian surface, which included these long, dark linear features, which Lowell claimed were canals. So according to him, Mars was this dying planet whose water was quickly drying up, and the alleged Martian civilization had dug these canals from the polar ice caps to their cities at equatorial latitudes in an attempt to transport water from the poles to the equator to sustain their continued existence. However, the Mariner 4 mission, which launched on November 28, 1964, definitively killed the idea of intelligent Martians when it returned the first close-up images of the red planet surface following its flyby on July 14th and 15th, 1965. The images that Mariner 4 returned were of this completely desolate planet with a thin atmosphere, a crater-covered surface, and no signs of liquid water or any civilization, either past or present. However, this did not completely end the idea of life on Mars, as our landed missions this day, including the Curiosity and Perseverance rovers, have continued hunting for signs of past habitability. However, the life that they are looking for is likely in the form of microbes rather than complex intelligent beings. It's also true that at the time of the Mariner flyby, there were some who argued that the resolution of the images returned by Mariner would not have revealed signs of humanity if the probe had looked at Earth. A couple of fun facts here about Mariner 4 was that each Mariner image took about 6 hours to transmit down to Earth, which is painfully slow by modern standards. These days, we can downlink many dozens to hundreds of much higher resolution images from the surface in a much shorter time through the Mars Relay Network, in which data from the surface is first uplinked to one of the spacecraft orbiting Mars. So that would be the Mars Reconnaissance Orbiter, Mars Odyssey, the Trace Gas Orbiter, and MAVEN. And then that data is then downlinked from those orbiters to Earth. Also, the processing of the raw data from Mariner was so slow that the team actually went out, bought a pastel painting set from a nearby art supply store, and then hand-painted a printout of the first image rather than wait for their computers to process it, which came with a sort of fun side effect of the image that they created being in color, while the actual processed image was in black and white.
Oh my gosh. I am totally picturing these scientists with their little pastel painting set, just having a grand old time, painting by number.
I mean, it really was basically like painting by number. They got their computer to print out the raw pixel values of every single image. Well, I guess it wouldn't necessarily be pixel values, but and then they assigned a color to each of the numbers and just painted according to that, and it actually looked pretty similar to the image that was actually returned once it was processed.
I love it so much. And also the kind of person every time I get to craft at work, I'm just yay, crafting time.
I occasionally wonder, like, was this something that they planned in advance, or like when they realized that the data was taking so long, like, surely we can come up with some better, faster way of doing this ourselves rather than waiting for the computer to do it for us.
I have no idea. Oh man, that's a question for the NASA History Office for sure.
Mm-hmm.
I like the idea of like, yes, those dark things on Mars, the canals.
Mm-hmm. Yeah, and as it turns out, those linear dark features weren't even real.
You know,
It was just really just sort of an artifact of the low resolution of the telescopes at the time.
bad telescope. But all the same, it's like kind of interesting that like, it wasn't wrong about the water disappearing. It's just wrong about when it was disappearing and what the context around the disappearing of the water was, which I find interesting.
Yeah, I did also read these papers from these people who were complaining about the resolution of the images, and it's really sort of very interesting because they're saying if you were to take the cameras on Mariner and point them at Earth, you wouldn't be able to see roads or cities or anything that says humanity is here.
That's interesting too. It's like this is not Google Earth.
Yeah, they're just like, sure, maybe we don't see any Martian civilization, but the camera is just such a terrible resolution that maybe it's just hiding behind all of these small number of pixels.
Well, I mean, we have since very much proved that there is no hidden Martian civilization. Probably one of those robots would have bumped into them at some point.
And we do have much, much better images of the surface from orbit now, too.
Oh, yeah. I do remember seeing one of those little, like newspaper cartoons or whatever, where it was like the rover is pointed in one direction, looking at like barren rock, and behind the rover was like a couple of little aliens giggling about like pointing and giggling, and like the huge city was just in the opposite direction.
I mean, they move. Those rovers move so slowly; it would not be hard to hide from them.
Well, I mean, they do see 360 degrees, though. And now we've got a helicopter, so.
This is true.
Helicopter that's still, like, up there and doing stuff.
I know,
it was supposed to last. So impressive.
Yeah, I did hear they just reestablished communication with it, too, because it apparently had, like, landed behind some ridge.
Oh, no.
That had blocked it from communication, but, the rover's now driven up behind that ridge, and they're talking again.
When Perseverance landed, this like a couple, like what, 3 years ago now, 2 years ago. My son was a few years younger, and he was so invested in this, and like everyone like sort of like personifies these things, right? So he was like, oh, they sent this thing. And he's like, and when it comes back, and I was like, oh, see, no, it's not coming back. And he bawled. He was so sad that we were abandoning this robot. And I was like, but it's okay. He's got a friend. He's got a little helicopter. And he was a little bit cheered up by that. And I did not tell him that we were only expecting the helicopter to last like 10 days or whatever, because I was like, it's going to break his poor little heart. But I'm so happy to see that 2 years on, little helicopter is still going.
It sure is.
Love it when spacecraft keep going. All right. Well, we move on to another spacecraft. This one going to the moon rather than Mars. So we're looking at July 14th, 1967, at the launch of Surveyor 4. This was the fourth lander in an uncrewed Surveyor program that was in preparation for the Apollo missions. And as I mentioned, it was sent to explore the surface of the moon. It was equipped with a TV camera, a surface soil sampler that looked a bit like, you know, those toys where it's like a bunch of bars that are kind of like arranged in an X, and like when you open them up, it stretches out to grab a thing, and then you like close them up and it comes back in with a claw at the end. It looks totally like a kid's toy. Love it. So it had a soil sampler and some strain gauges on the landing legs, because there was still some question as to like how solid or floofy was the regolith, and had like numerous engineering sensors. And also in the soil sampler, there was a magnet to figure out like, do we have ferrous elements in the regolith? So the mission objectives, so the primary objectives were to perform a soft landing on the moon in a section called Sinus Medii, which is sort of in the, like if you're looking at the moon, like in the center of the visible part of the moon. And to obtain some television images of the lunar surface. And the secondary objectives was to use the soil sampler to manipulate the lunar surface material while being observed by this television camera, as well as obtaining information on the bearing strength, the radar reflectivity, and thermal properties of the surface using the array of engineering sensors. The flight to the moon was flawless. Unfortunately, contact was lost with the spacecraft about 2.5 minutes before the expected landing on July 17th, when the craft was about 15 kilometers above the moon's surface. At first, it was thought that the craft had landed successfully, and they tried for 34 hours to just keep sending commands and to reestablish communication. They sent 4,255 commands and no deal. There was a lack of evidence as to the source of the failure, but you know, they struck a committee and hummed and hawed over it and came up with 4 possible causes. One was a breakage of a critical power lead in a wiring harness, or a failure of the connector or solder joint. The second was a rupture in the case of the retro rocket, which would have caused the retro rocket to explode, because the communication was lost just before the end of the burn of the retro rocket. And the third possibility is a failure of the transmitter, which caused its power to drop to 0, or fourth, a sudden failure of a pressure vessel, like a propellant, helium or nitrogen tank, something like that. We'll probably never know what happened to it, because it was just kind of like, we hear it, and now we don't. We don't know.
Yeah, I do think it's interesting that we still don't know what happened to it, because I would think if it had landed, whether that be a soft landing or a hard landing, we would be able to see it with the really high resolution imagery we have from the Lunar Reconnaissance Orbiter now, like we did for that Japanese lander that crash landed like a month or so ago.
Yeah.
So the fact that we don't see anything, to me at least, makes it seem like maybe it did explode at some point above the surface.
And I think I was looking at different sources about it. One source gave me like these 4 things, which was like the more detailed source. The less detailed source were just like, meh, probably exploded. Mm-hmm. So, I mean, seeing as there isn't like, oh, look, there it is. I think that's why most sources are just like, yeah, probably explode.
Yeah, I mean, the Surveyor spacecraft were pretty primitive, at least by modern standards. But a little fun fact, I think, is that I'm pretty certain one of them was the first to be returned at least partially intact from the moon back to Earth. I think it was Surveyor 3, because Apollo 12 landed just a few hundred meters away for where
Yes.
Surveyor 3 landed, and so the astronauts went over, ripped off its arm, and brought it back with them to the Earth.
Yes. Do, do, do. Yoink. I'm bringing this home. That's
I
kind
guess
of
it's
funny.
not doing anything else.
It's true. Why not? Go stick it in a museum. I support this. Yeah. Yeah, I think you're right. I think it was Surveyor 3. And I think there were 7 surveyors in all. I think it was 6 that landed kind of close to the same area, but I wasn't able to find like just how close and if it was able to like gather any information as to like what happened to this one. I think they were just kind of like, oh well, carrying on. We're
That
trying
sort
to
of
get
was,
to the moon in this decade, and we've got 2 years left. Let's go.
yeah, that sort of seemed like how that sort of era was. Like, yep, it blew up. Let's just immediately turn around and send another one.
Yeah, pretty much. Gotta get there before those Russians. All right. Well, from one possible explosion to some impacts.
Sure. So this is a slightly more recent event. This occurred on July 16th, 1994, which is when the first fragments of comet Shoemaker-Levy 9 impacted Jupiter. So, as the name suggests, this comet was the 9th co-discovery by astronomers Carolyn and Eugene Shoemaker and David Levy, taken with the 46-centimeter telescope at the Palomar Observatory, which is located near San Diego. And they discovered this comet on March 24th, 1993. So, shortly after they discovered Shoemaker-Levy 9, they pretty quickly noticed some fairly unusual things. First of all, the comet appeared to be elongated rather than centrally concentrated. It covered an area of the sky about 50 arc seconds long and about 10 arc seconds wide. This is about the same width as Jupiter appears in our sky at opposition when it is closest to Earth. Second, calculations of the comet's orbit showed that it was gravitationally bound to Jupiter rather than to the Sun. Taken together, these 2 facts suggested that the comet had been captured and then fragmented by Jupiter at some point in the past, possibly in the mid-1960s to the early 1970s. So as more observations of Shoemaker-Levy 9 were conducted, its orbit was further refined. Eventually, enough data had been gathered that predictions of its future motions concluded that in July of 1994, it would pass within 45,000 kilometers of Jupiter's center. Jupiter has a radius of about 70,000 kilometers, so this put the comet's perigeo well within the planet itself, meaning that Shoemaker-Levy 9 was on a collision course with Jupiter. So the near inevitability of the collision was very exciting, as astronomers had never been able to observe 2 objects of this side collide with each other in near real time. Adding to the excitement, the impact was expected to pull material from deep within Jupiter's atmosphere up to the surface, allowing for studies of the interior of Jupiter to be conducted in a way that had never been possible before. So on July 16th, 1994, just about every telescope in the solar system was pointed at Jupiter. This included both amateur and professional observatories on the ground, as well as space telescopes like Hubble and spacecraft like Galileo, Ulysses, and Voyager 2. So at 4:13 p.m. Eastern Daylight Time, fragment A of Shoemaker-Levy 9 slammed into the Jovian atmosphere at 60 kilometers per second, creating a 3,000 kilometer high fireball that reached temperatures up to 24,000 Kelvin, which is over 4 times hotter than the surface of the sun. The impacts continued on until July 22nd, leaving a chain of dark splotches on Jupiter, some nearly the size of Earth, and these would last for a number of months. So this is not actually the most recent time that a large object has hit Jupiter. Most notably on July 19th, 2009, almost exactly 15 years after the Shoemaker-Levy 9 impact, an undiscovered asteroid likely about 200 to 500 meters in diameter plunged into the atmosphere, creating a dark spot roughly the size of the Pacific Ocean. And since this 2009 event, there have been about 9 additional observed impacts, most recently in October of 2021.
Whoa. Yeah. That image of like those dark splotches is kind of like
Hmm.
seared into my memory.
I mean, it really also shows off, I think, the challenge of trying to find these really small objects, even in our own solar system, because other than Shoemaker Levy 9, the first indication that we had of their existence was when they were obliterated by Jupiter.
Yeah. And so, did I understand what you said right? Like, they were fragmented in the 60s to 70s. So, like, this was a fairly short period comet,
Hmm.
and it wasn't discovered till the 90s.
Yeah, I mean, it wasn't like a terribly bright comet either. Because I mean, it's still out there near Jupiter, so it's not terribly close to the sun. Um, so I mean, they just happen to be conducting this survey of these transient objects, and they're like, oh, this is a comet. Oh, it looks really close to Jupiter. Oh, it is near Jupiter.
Oh, it's in Jupiter. I don't know. I just find it interesting that, like, because I mean, people have been looking for comets forever, right?
Hmm.
That it wouldn't have been discovered before the 90s.
Yeah, I
Interesting.
mean, we think of like the really impressive comets, but not all of them are these really huge ice dense things that will produce these brilliant tails. Some of them are just really super tiny, like a couple dozen meters across, or dirty ice
Oh, yeah.
floes that are just barely visible at all.
Fair, fair. Yeah, I still have my copy of STEM News magazine with the photo somewhere in my house. Yeah, this was around the time where I was starting to get back into astronomy. There are like 3 times. So like grade 1, when I first learned about astronomy, I was like, ooh. Then there was grade 6 when I was like, I'm going to be an astronomer. And then there was in high school and I was like, I'm really going to be an astronomer. And I was like, yeah, this was that period.
Mhm.
I didn't really know about some more of these recent ones though.
Yeah, I mean, it's like they've been sort of coincidental. Someone just happened to be looking at Jupiter, and it's like, oh, that's not supposed to be there.
Yeah. I mean, I was a little busy in 2000. I had a little tiny baby.
Hmm.
I was otherwise occupied. All right. Um, let's do our last item for this week in astronomy and space history. So we are going to July 12th of 1988, the launch of Phobos 2. And this was the last space probe that was designed by the Soviet Union. It was designed to explore the moons of Mars, Phobos, and Deimos. As I said, launched on the 12th of July, 88. It entered orbit on the 29th of January of 89. It operated nominally throughout its cruise and Mars orbital insertion phases, gathered data on the Sun, interplanetary media, Mars, and Phobos, and investigated the Martian surface, the atmosphere. It returned 37 images of Phobos, which is about 80% of the moon, which is cool. And shortly before entering its final phase of the mission, during which the spacecraft was supposed to approach to within 50 meters of the surface and then release 2 landers, one which was supposed to be like a mobile hopper, move around the moon, and the other one was the stationary platform. Contact with Phobos 2 was lost. And then the mission ended when the signal failed to be reacquired by the 27th of March of 1989. The cause of the failure was determined to be a malfunction with the onboard computers. So problems with the computers started developing during the interplanetary flight. And by the time that the probe reached Mars, 2 of its 3 computers were not working properly. One of the computers was completely dead, which was okay because there were another 2. Unfortunately, the second one started to malfunction, and that was a problem because the probe worked on a system where its computers voted on any decision. And so with only one healthy computer, the healthy one could not control the craft because it was unable to outvote the 2 dead ones. Lost every vote. And also the craft's high-speed transmitter had also developed some issues. But despite all that, it successfully carried out 3 preliminary encounters with Phobos, during which it imaged the moon with video spectrometric camera. That's a really long word. And combined radiometer and photometer for Mars, and the imaging spectrometer for Mars. As I mentioned, it imaged 80% of the moon, and the infrared spectrometer found no signs of water. So not a complete success, but also not a complete failure.
And there is an upcoming mission that is going to carry on the legacy of Phobos 2, which is the Martian Moons Exploration, or MMX, which is being developed by Japan. It's supposed to launch next year.
Nice.
Yes, they're going to be, actually land on Phobos and collect a small sample and send it back to Earth.
Ooh. I find that interesting. It's something we'll talk about later. There's a tease for you folks. Yeah. Cool.
Yeah, also, the reason for this sort of computer voting system is also interesting, because, the radiation environment in interplanetary space is pretty harsh. And so you can have things like, high energy cosmic rays can strike your computer and cause things like bit flips, which can have unanticipated consequences on your spacecraft. So before they could create these sort of radiation-hardened CPUs that we use these days, they had the system where they just had multiple computers under the assumption that they couldn't all fail at once.
Oops. I mean, at least it failed later in the mission, and some interesting science came out of it. I also find it interesting, that the targets were chosen because I read this somewhere. It's like these targets were chosen because they didn't want to compete with the NASA missions. It's like, you're going to Mars. We'll go to the Mars moons.
Mm-hmm.
The original launch date was supposed to be in '86, but it got delayed a little bit.
And you could have a bit more time to work on those computers.
Maybe. What you're saying about the computers makes perfect sense. It just needed, a backup system.
A backup system for the backup system.
Well, what happens if the other computers are dead?
Mm-hmm. Yeah, that seems interesting that it would not be able to outvote a dead computer. You'd think if it was dead, it would just be sort of removed from the equation.
Yeah. I am not a 1980s computer engineer, so I have no insight into that. All right, folks, you are listening to York Universe, broadcasting live from the Allan I. Carswell Observatory and located at York University in Toronto, Ontario, Canada. If you want to join us in the online public viewing, head over to www.yorku.ca/science/observatory. And you can join in the chat, ask questions, etc. over there. You are listening to Julie and Connor. We have just wrapped up our This Week in Science or Space and Astronomy History. And we are now going to head into our news items. Why don't you start us off, Connor?
Sure. So this is a fairly hot off the press release just from a couple of days ago, talking about gravitational waves. So, just as, again, a bit of background, so these gravitational waves are a consequence of Einstein's general theory of relativity. As objects with mass move around, they will actually generate ripples in the fabric of space-time. So the existence of gravitational waves was first confirmed in 2016 by the LIGO-Virgo collaboration, which used lasers to very precisely measure the lengths of two tubes which were positioned at right angles to each other. As gravitational waves pass over the observatories, the lengths of the two tubes change ever so slightly, which can be detected as a change in the way that the two lasers interfere with each other at their intersection. So this first successful detection was of gravitational waves generated by the merger of two about 30 solar mass black holes approximately 1.3 billion light years away. Since this first detection, there have been about 22 additional detections of these binary merger events, which can be between two black holes, two neutron stars, or a black hole and a neutron star. Gravitational wave observatories like LIGO are sensitive to black hole and neutron star mergers due to the incredible masses of these objects. In the final moments before merger, they are moving with such speed that the gravitational waves that they generate can be detected across the universe. However, there has been a long-standing theory of the existence of a gravitational wave background formed of long wavelength, low frequency waves caused by many events blended together over the life of the universe. Unfortunately, the long wavelengths and low frequencies mean that this background signal cannot be detected by observatories like LIGO. Down to the gravitational wave background, the American Nanohertz Observatory for Gravitational Waves, or NanoGrav, turned to a different detection method, specifically pulsar timings. Pulsars are neutron stars that rotate, which launch beams of radio waves across the universe that can be detected as radio pulses as the beam sweeps across Earth. The frequency of these pulses is very precise and regular, so any changes in their period would be unusual. The gravitational wave background would stretch and squish space-time between us and the pulsar in an irregular, unpredictable way, which would cause the radio signals to arrive either a little bit earlier or a little bit later than expected. If we can measure the variations in the periods of many pulsars at once, 67 in this case, then we can theoretically measure the existence of a gravitational wave background. And this is exactly what NanoGrav has done. After 15 years, enough data has been collected to confirm that the predicted gravitational wave background does in fact exist. It was an incredible effort combining data from radio observatories like the Green Bank Telescope in West Virginia, the Very Large Array in New Mexico, and the former Arecibo Telescope in Puerto Rico, turning them all into a single gravitational wave observatory larger than our solar system. It is believed that the measured signal was created by many supermassive black holes orbiting each other and then merging over the spatial and temporal extent of the universe. Each pair creates waves at its own frequency, all mixed together to produce this gravitational hum that was detected. So as these data are analyzed further, they could help us answer some of the many open questions about our universe, including how it has evolved over time, how often galaxies collide, and why black holes merge at all. It's even possible that some of the background is made up of gravitational waves emitted in the moments after the Big Bang, which would allow us to probe the very first few moments of the universe in a way that has never been possible before.
This is so exciting.
Everyone was super excited leading up to the press release. It was just sort of all over Twitter. Everyone was like, we need to look out for this because it is going to be one of the most foundational discoveries in physics of this century.
Yeah. All I saw was a very excited Hank Green. And then I forgot to go look into it, so I'm so glad you brought it up tonight.
Yeah, it's truly like an incredible effort. Like 15 years of data collection is really something.
Yeah. And I don't even want to think about the analysis space.
Yeah, because they're like these waves are apparently just like so low frequency that to confirm that they are happening, you do in fact need to listen to them for 15 years because they're that low frequency that a couple of wavelengths will take you 15 years to detect.
Whoa. That is a lot of radio data.
Mm-hmm. Yeah, interferometry, radio interferometry is really, I'm never not impressed by it. Just taking a whole bunch of telescopes all around the world and being like, you are now one huge telescope.
Yes. And I understand how that works over like a 12-hour period.
Mm-hmm.
I do not understand how it works over a 15-year period.
Yeah, I would not want to know how much data they had to sort through. 15 years, like multiple observatories.
Yes, my brain is unraveling right now. Yes, I worked on some radio data in my summers when I was an undergrad, and it would come in on these tapes because there's too many terabytes of data. The internet could not handle that. You had to have your data shipped to you.
I'm pretty sure that's still the fastest way to transfer large volumes of data.
Yeah. And then you would put these tapes, these high density tapes into the machine. And then you would walk away and do something for several hours while it was loading everything into the computer. And that was for 12 hours of data.
Mm-hmm.
This is not computing in my brain. How?
Definitely take a whole team of people to analyze sort of that volume of data and to, figure out what it's trying to tell you.
And how often are they looking at the pulsars? Yeah, and they're obviously not always looking at the pulsars.
Mm-hmm.
Whoa,
it's not
I
like,
need to go
it's not like it would be really obvious changes in timing either. We're probably talking about milliseconds to nanosecond changes in the timing of these pulses.
Man, how do you go from this is significant to it's noise? Oh, this got from very exciting to very mind blowing to amazingly exciting in the space of 10 minutes. Awesome. Thank you for bringing this piece of news this week. Would love it. Now I'm going to bring the mood down with the next piece. We're going to talk about cost overruns and estimated costs of a Mars sample return. Recently, Richard Cook, the program manager for the Mars sample return mission at the Jet Propulsion Laboratory, and Jeff Gramling, the director of the mission at NASA headquarters, met with NASA leaders to brief them on mission costs, and the expected price has doubled from $4.4 billion to an estimated $8 to $9 billion. And that price tag does not include launch costs or operating costs over a 5-year period, nor the construction of a new sample receiving facility to handle rocks and soil from Mars. So all told, the total cost of the Mars sample return mission is now about $10 billion. And that's about the same as JWST at launch. So NASA and ESA and the scientific community have wanted to return the samples from Mars for a long time. This would help us understand geology and look for evidence of past life and possibly even present life, though not big civilizations. And the current design was settled on last summer, and under this plan, NASA will develop a large sample retriever lander that's due to launch in 2028, which is not long from now. And after, so this is how it would work. So your sample retriever lander goes to Mars. The Perseverance rover, which has been collecting and storing samples of dust in these 38 titanium tubes that it has on board, and they're all size of large. They're each size of a large hot dog, and it will bring samples to the lander. Now, as we mentioned, Perseverance has been on Mars since 2021, and NASA decided that it's a little risky to count on that rover still working when we get there, a decade after it's gotten there. So, well, we should probably send a couple of helicopters, like Ingenuity, to like be the backup plan to go retrieve these samples. The sample tubes will be placed on board a rocket called the Mars Ascent Vehicle that's being developed by Lockheed Martin, and it will be stowed inside the lander. And after launching from Mars, that rocket will release the orbiting sample container into Mars orbit. And that container will be picked up by the Earth Return Orbiter that's to be built by the European Space Agency. And that's going to bring the samples back to Earth, where they're going to be released into a small spacecraft to land on Earth. This all seems very complicated. If the launch happens in 2028, samples could be returned by 2033. But from what I've read, no one expects this to actually happen. Even 2030 seems like a stretch for the launch of this mission. So what's driving up the costs? The original concept involved sending a single lander with a rover to fetch the samples from Perseverance. Apparently, the depth of that analysis was insufficient, included a bunch of errors. For a while, a second lander was added to that plan, and that increased the cost by more than $1 billion. On top of that, there were some management problems at JPL, including staffing issues that delayed the Psyche mission, which we may not have time to talk about, but maybe we'll get to that in the next show. An independent review found that JPL has taken on an unprecedented workload without having the resources to complete major projects. And JPL has never built a lander this large or complex. It'll be the size of the two-car garage. So some are suggesting that maybe they should leave this to like the private companies that have a lot of experience, especially given that much of their staff will be working on the Europa Clipper through most of 2024. And anyway, so this will undoubtedly lead to even more cost overruns. The project is projected to cost $1 billion a year. NASA's planetary science budget is about $3 billion a year for the rest of the decade. So we're looking at a third of their budget on this one project. And the project hasn't even reached the preliminary design review stage, in which a formal analysis of the mission and its design will be performed. And many missions costs grow after that phase. The project is a high priority for the planetary science community. However, cost overruns could be detrimental to the community if money to cover the cost is going to come from other missions, affecting, quote, the balance of the planetary portfolio. If the cost exceeds certain thresholds, the decadal survey report suggested asking Congress for more money rather than taking money away from other programs, which I imagine would be a hard sell. Some fear that this project will become the planetary science community's equivalent to JWST as far as like cost, and oh my goodness, it's costing so much and taking so much time. But Whereas, like, no one can say JWST hasn't been successful. It's providing data for a really wide swath of scientists, and Mars samples would be very costly, but benefit a very small segment of planetary scientists. Planetary science community has already started feeling the effects with missions like Veritas, the mission to Venus being delayed by 3 years. The Dragonfly mission to Titan is getting less money than is needed to launch on time. A planned orbiter or proposed orbiter to Uranus might get pushed. So what are the options? Contract the lander out to the private sector, and it's also been suggested that the helicopters are an expensive backup plan that might not be necessary. So maybe not have those for now till you know that you need them. Thomas Zurbuchen, who left NASA at the end of last year after 7 years leading its science mission directorate, is quoted in the article I read saying, quote, "If the answer is this is not the decade to do it, my heart breaks because I put so much effort into it. But it is better to not do it than to torch the whole science community. If we have to have the courage to say no. That's the only way we earn the right to say yes." End quote.
Yeah, this is definitely becoming a very controversial mission in the planetary science community. Like, it's definitely alarming that it is already at the same cost as JWST when JWST's cost increased by about 20 times over its development mission. So the fact that MSR hasn't even been through preliminary design review yet, and it's already at JWST costs is very concerning, and the sort of knock-on effects it'll probably have for other missions later in the decade.
Yeah. And I can see, like, everyone's going to be watching this Japanese mission to the Martian moons, see how they're doing it. This also seems like a very complicated plan. So we're going to send the thing down, we're going to put the thing in the thing, and put the other thing, and send back and put it in the other thing, and the other thing, and then the other thing's going to come back. It's like too many things.
Yeah, I mean, personally, I'm always a proponent of, I think, sending more cheap things to a variety of places than like one really expensive thing to one place. But I guess we'll see what happens in the coming years. I have the feeling that more people are going to be like, maybe we should take a second look at this. But I don't know, maybe they'll pull out some miracle and be like, oh, actually, it's not going to be $10+ billion.
Yeah, I don't know. This whole thing has had me scratching my head from the beginning. So it's like, ever since I read it, like, Perseverance is collecting samples for a mission that hasn't been planned yet. I'm like, wait, what? We're doing what now?
Yeah, it's one of those things that's been like an idea that's existed for like 20 years. I mean, Curiosity was supposed to be the one collecting the samples, but then that fell through. So I think this is, it's been an idea that's existed since like the early 2000s, and this is the closest we've ever gotten. But it seems increasingly unlikely that it'll be able to get to the finish line, I think.
Well, from my understanding, those little containers are built to last. And it's not like Mars is running out of dirt.
This is true.
I guess the idea is like, this is another step about learning in Mars before sending people to Mars.
It's like it's being advertised as the mission that could discover life on Mars. But like, if I'm going to be spending $10+ billion on something, I think I would want my chances of success to be slightly higher than it's not literally impossible.
Oh, I can already hear the people saying, We have so many better things to spend $10 billion on Earth. To which my answer is usually like, where do you think this money is going? Like, it's keeping people in jobs. And when people earn money, they buy things. And, like, it's not like the money, like, we're not putting the money in a rocket and sending it into space. So I don't necessarily, like, see that argument as, like, one that holds water, but I kind of start hesitating when it's like, oh, we've got this half-baked plan.
I think we could. I think there are better ways to spend $10 billion in space.
This is it, exactly. There are ways to get more bang for our space buck.
Mm-hmm.
Especially if, like, anything goes wrong.
Yeah, that's definitely the additional challenges. Something of this scale has literally never been done before, so it's a lot of money to pour into something that is very, very risky. With all of those moving parts, like a failure of any of them would mean, a failure of the mission.
Yeah. Yeah. Oh boy. All right, we've got 4 minutes. Do you want to talk about Psyche or Ariane 5?
I can probably speed through Ariane 5 real fast in those 4 minutes.
All right, let's do it.
All right. So the Ariane family of rockets has been the primary launch vehicle for the European Space Agency since the first Ariane 1 mission in 1979. Of the 5 variants, Ariane 5 has been 5 rockets. First launch taking place in 1996. Incredibly reliable. Failure. This includes 83 consecutive successful launch streams between April of 2003 and December of 2017, ending with the partial failure of the VA-241 launch in January 2018. However, the satellites it carried still made it to orbit, so the last total failure took place in December 2002. The most notable spacecraft carried by Ariane 5 was JWST in December of 2021. The excellent performance of the rocket was estimated to give the telescope an extra decade of useful life, as much less of its propellant was used to correct its post-launch trajectory, allowing more to be reserved for station-keeping maneuvers. So the recent retirement of Ariane 5 actually leaves ESA without its own launch solution, as the successor Ariane 6 rocket is not expected to be ready until early 2024, similar to the situation the US faced with its manned spaceflight program after the retirement of the space shuttle.
Yes. Well, I mean, at least it's only a 6-month.
This is true, yes, assuming that Ariane 6, is
it
ready.
Stays on schedule. Yeah. It's interesting. I've never paid that much attention to rockets.
Mm-hmm.
Like, I know the names. But I always kind of like glaze over when it's like such and such a thing was launched on this kind of rocket. I'm like, yeah, whatever. Moving on. What did it do once it was already in space? What interesting things did it learn? That is quite the reliability.
Sure is. I think that's a big part of why they chose it for JWST.
Yeah. That's fantastic. Congratulations. Ariane 5. Beautiful. All right. Folks, you have been listening to York Universe, the astronomy and astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. Your hosts this evening have been Connor Hayes and myself, Judy Tomei. Stay tuned because it is science night in Canada. Coming up next is Western World, Quirks and Quarks, and Science for the People. You can always connect with us on Twitter, Instagram, Facebook. Check out our website. Thanks for tuning in, and clear skies, and have a good night.
Good night, everyone.
We hope that you've enjoyed this program from AFM Radio, the broadcast service of Astronomy.fm. This program has been released under Creative Commons license. Please contact us for details. You may find more of our AFM original programs on our website. It's really easy to find us. We are Astronomy.fm. You may also find us in the iTunes radio listings near the top of the News Talk section, and also as an iTunes podcast selection. We'd love to hear your comments. Please email us at radio@astronomy.fm. Thanks so much for being part of the voice of astronomy around the world and across the known universe. This is Astronomy.fm Radio.